Good morning. I hope a lot of you enjoyed yourselves last night if you came to our party that we had to kick off the summit. And if you didn't, I'm sorry, and maybe we'll see you next year if we make it an annual thing. So, and thanks for coming. But I hope you didn't drink too much last night, because I'd actually like to get your attention and focus here, because I think we have a problem, a disconnect in RISC-V. And actually, as I was watching the previous speakers, I think about a third of you are probably playing on your phones or doing some emails on your computer. So for the next 10 minutes, I'd actually like your attention here, if you could, because I want to talk about this disconnect that we have in RISC-V and how we can collaboratively address it. So I like big numbers. I'm a data type of guy. And there's one number that's quite a challenge for all of us: 1,000 million million. That's a quadrillion, 10 to the 15. That's the number of verification cycles it takes ARM when they're verifying a core. 10 to the 15, that's a huge number. And we're going to come back to that number in a bit. So, RISC-V disconnect. When you're a core user, you're using a core, RISC-V core, you expect it to have quality. And you expect it to have the type of quality that you would have seen from previous IP providers or core developers. And this is the disconnect, this is the challenge here, is the resources it takes those companies to build that verification technology and do that verification is huge. And it's highly unlikely that there are many RISC-V core developers that will have those resources. And that's the disconnect, and that's the problem we've got to try and solve collectively. And we've got to try and work out how that we can take and understand what was a proprietary verification methodologies and technologies and experience and tools, and get those into the RISC-V community so that we can produce these high-quality cores. And that's really what I'm going to talk about, how we can improve and increase the quality of RISC-V processes using verification standards and advanced methodologies. So, when we started Imperas some 15 years ago, we were seeing that electronic products were just starting to be defined by their software. And it wasn't just the large application processor. And now everything is controlled and defined by software. Everything is run by small processors or application processors in the system. And it's now becoming more than a device problem, it's becoming a systems problem where everything is interconnected as well. So we have a lot of challenges in that type of ecosystem. And I think if you listen to the presentations yesterday from Callista and Mark, we're focusing on the ISA, we're focusing on the software, as was mentioned this morning again by Callista. And absolutely, they're essential. But the challenge is, if we build devices that don't do as we need, and they don't work, and there's fragmentation in them, then the systems are going to fail. And if the systems fail, we have a problem. So I believe that there's this third challenge, this third ecosystem, which is verification that's required across the industry in RISC-V. So let's get back to the big number, a quadrillion, 1,000 million million. And this is from a paper that ARM wrote a few years ago talking about their whole verification strategy. And actually, it wasn't 1,000 million million, it was 2.1 thousand million million, as it turns out, the verification. Put that in context. If you have a system Verilog simulator that runs at that sort of speed, you'll need 15,000 of them for a year to get to your 10 to the 15 cycles. That's just mind-boggling. If you use an emulator, hardware emulator or FPGAs, okay, they might run 50 times faster, so you need 30 years on one of them. Now, obviously, that's for a state-of-the-art, high-end application processor. If you're doing embedded stuff, maybe you can do it in an order of magnitude less. And so, you can have 1,000 simulators running for a year. And actually, many projects are sort of 2 years for verification. So it's not unreasonable. You just got to get the resources to do it. And the way that they do it is two ways. One is they license in technology, if it exists, or they invest in it. But they have huge teams, so it costs hundreds of millions of dollars. And you have teams of 100 type of people doing the verification in there. And of course, in the past, that's been for ISAs that have been fixed and controlled by one vendor. The challenge we have in RISC-V is that pretty much everybody can extend it and evolve it. And that's actually one of the fantastic benefits of it, this freedom to take it further and take it where you need it to go. And so that, there is a big challenge out there. Now, what did they spend this hundreds of millions of dollars on, and what do they have these people doing? Well, there's actually a whole bunch of stuff that's needed. The tools, the verification IP, models, methodology, infrastructure. It just goes on and on and on. And actually, there's a lot of people doing stuff with formal tools and correct by construction, and lots of challenges, lots of work that needs to be done. And if they couldn't buy it, they built it internally. So there's a lot of money needed to buy technology, a lot of money needed to invest in people to do it. So it's a big challenge, I believe, in there. And so we have to accept that RISC-V has this problem, this break here. And the problem, I believe, is verification. Now, life's tough, right? Most ICEs are no longer used. And actually, when looking up to do this presentation, I looked and just online, I think I found 77 different companies and entities that have promoted ICEs, and some of them had 20 ICEs in their history, like Digital with DEC and stuff like that. And so we have to see that there's a lot of challenges in adopting ICEs, and most of them are no longer used. And actually, most chips are fabricated with errors in them and fail. And most semiconductor startups actually don't bring a good return to investors. So it's nice to hear Lip-Bu talking about investing in technology in the space, but it is a real challenge. So even if everything's working, life is tough. And that's what we've got to try and improve what we do in the RISC-V world. And back to the big number, we've got to say that, realize that there are some companies that can afford to invest in this, but most can't. And the value in RISC-V is it gives this freedom to everybody. And so we have to realize that, companies like ARM and Intel, they have huge revenue streams for licensing their proprietary ISA or selling their silicon. And we don't have that benefit in RISC-V, so we've got to do something differently here. I think there's three things that we can do. We can partner and collaborate in areas that are non-competitive, that aren't our differentiation. We can try and get technologies in the market that we can license and share the cost with the rest of the ecosystem in there. And then we can try and build standards to make things reusable and make people more efficient in there. And so there's a variety of different things. And I think the key thing is if it doesn't differentiate your company, your product offering, then you should be collaborating or using tools. Obviously, as a tool vendor, now I'm going to just give a little plug about commercial tools, as that what we do in Imperas. And so a bit of our history, when we started Imperas, we focused on the ICEs of the day, and our focus was to build world-class modeling technology, simulation technology, to help people develop software. And we built a good business around different ICEs, and I think we support now something like 15 different ICEs in there. And it was a good growing business. 2016, I remember being at the Design Automation Conference, and my VP of Sales, Larry, who hosted the party last night, said, oh, there's this stuff from Berkeley. You should go. Well, he's a Berkeley alumni, so he would say this. But he said, go and listen to this guy talking about this new processor technology. And actually, several people in Imperas are actually alumni from Berkeley. But I went, and I thought, OK, that's interesting. We built a model in 2016. And by 2018, we were a bit surprised that we had people licensing our models, and really not for software development, but actually for hardware verification. And they would, because our models are very controllable, very configurable, extendable, and people were using them for RISC-V, and we realized to help do verification. And so for the last 4 years, we've really been involved in the verification bit of RISC-V. The last 3 years, we've been involved with an organization called OpenHW, which is building open source cores, but to high quality. And for the last couple of years, we've been working on sort of standards to try and make it more efficient to reuse verification technologies and to also look at advanced verification methodologies. What have we learned? Okay. Now, a lot of people get confused about verification and compliance, and actually there's a good talk, I think it's tomorrow, with the chair of the RISC-V architectural compatibility group, where we're talking about the continuum between compliance and verification, or compatibility and verification. But we've basically, over the last 4 years, been trying to understand what it is that people have to do, because until RISC-V, most verification was internal and proprietary of process to the IP vendors, ARM and Tensilica and ARC and stuff like that. And so we've looked at this and thought, okay, what are the different levels? So we've sort of identified 3 different levels of verification that people do. And the bottom level really is sort of simple test. Does a program run, or does it get a result? Which is a way very good for if you're building something, you want to just check that it's working for your own uses, maybe in academia or a hobby or something like that. But if you want other people to use it, you need some form of compliance or compatibility checking in there. And there's techniques people use there where they create a signature file or a trace file and then compare it after simulation. And that allows you to see things around the edge, but doesn't really let you see what's going on inside the devices and the pipelines. And so it's not verification. So it's good, again, for probably internal uses, but you've got no idea it's really going to work in real systems and other people's software. So the third layer, the most complex layer, is real sort of verification here. And there's technologies that people are involving where they lockstep and co-simulate between models and their Verilog and stuff like that. And so there's a variety of different ways, and they're all good, but it depends what you're trying to achieve with your device that you're building, of which one you really should be adopting and the resources you've got. Obviously, you know, the quadrillion and 10 to the 15 is a clear verification. You know, if you're going to try to do that much verification, you know, you're at the high end looking for something which is going to work across the industry for a variety of different people. So that's what we've learned in terms of some methodologies that people learn. And what sort of tooling are people going to have to get in place for this? And you know, this is just a list of some of them that we've gone through to work out. And some of them are industry generic, like regression testing and, you know, continuous integration or whatever. Some are industry standards, like the HDL simulators. Some are bespoke to the ISA. And we can sort of start leaving these to other groups. Like we can leave the industry stuff to the EDA vendors. We can leave the ISA stuff really to the software teams and the software ecosystem that we hear about with the RISC-V. We can think of the formal tools. There are people working on that, and as the sale model evolves, we expect to see formal tools come out of that, but it's early days for that really now. And tests, people can develop their own tests, but they're very core, bespoke, and specific. And the 3 areas I want to sort of consider a bit more detail is the test bench, the frameworks, the models, and then the tooling that sits around it to help you with the verification. And the challenge that we have is that these need creating and adapting for each of the cores that's been verified. And that's part of the challenge is, yes, you could do it for one. It might take you several years and a lot of investment, but then you might have other cores you need to do in your company. So we need to find ways that allows us to reuse things and configure them and develop them so that we can be much more efficient. And that's where standards come in. And just as an example here, as I said, we're involved with the OpenHW group building open source cores. When we started doing verification with them 3 years ago, early 2020, late 2019, you know, what we did is we built an environment, system Verilog environment that had the core in it, had some technology and IP in it, verification IP, including a reference model in there. And it worked very well. The core got to met its goal of getting to RTL freeze when it wanted to with very good coverage and everything. But the challenge is, an OpenHW roadmap is that they've got many cores that they want to do. It's not just one. So they don't really want just an ad hoc test bench and environment in there. They need something which can handle all of the different cores. And so what we did was we did some work and came up with some standards. Well, it's really one standard with several bits. And there's talks on it later this week that you can have a look at. But the key thing is it defines interfaces between the core on one side and the reference model on the other, and the test bench in the middle, so that if you implement to those interfaces as standard, you can reuse things. So you could switch out your reference model. You could change your design under test to a different one. And the only bit you really need to do from project to project is to define this tracer if you're adopting this interface, this RVVI interface. And it's public, it's open standard on the GitHub there. But the key thing is that if you're doing verification and you implement this tracer to this standard, you can reuse things. And that's the key thing. And one of the things that you can reuse, for example, is functional coverage. And if you're involved with a RISC-V core and having to do functional coverage in Verilog, you'll realize that you might have tens of thousands of lines of this stuff. And actually, it's not differentiating you at all that you've got this. It's the same for every RISC-V 32i or M or C. The same functional coverage will be needed for the architecture. Yeah, you might need some specific stuff for your specific pipeline and microarchitecture in there. But there's 40,000 odd lines of code in the sort of system Verilog functional coverage you'd need just to check that you're testing the right sorts of things. And so we've got this project going in OpenHW to come up with the requirements for this functional coverage, moving from architecture into microarchitecture. So it's looking for things like, if an interrupt happens on a certain instruction, where it happens in the instruction, if you've got a multi-cycle one, and to verify that, have you covered that and things. So there's lots of different areas of functional coverage, but we can generate these from a machine-readable form, and then it can just plug in because it hooks into this RVVI trace. So you don't have to build this 40,000 lines of system Verilog. It's available to be reused and configured for different projects. And all you need to do is do the trace from your core into this verification environment in there. And so really to wrap up here, summary that the processors, RISC-V, for it to fulfill the destiny that we hope that it's got, we've got to improve the quality. They've got to be high quality. And high quality means you've got to use a lot of verification resources in there. You can't just hope. And you need to improve the verification methodologies you've got. High quality needs better verification methodologies. And a key thing for reuse and efficiency is to use standards. And I think that that's what we've got to sort of call to action for the industry, is that we've got to try and not just focus on the ISAs and the software, we've got to focus on the verification as well to fulfill this. So, because if we fail in this verification challenge, then RISC-V won't achieve its potential. And collaboration is working really well, I think, in the ISA, in the evolution of it, and it's really working very efficiently and quickly. Also in the software world, it's huge challenges for sure, but we have to do a similar thing in the verification space in it. And we're starting to do this in the collaboration we're doing in the OpenHW group, and it's interesting. It's people that aren't trying to use the cores from the OpenHW group that are also getting involved because they're seeing that they can collaborate on these verification ecosystem space. And we're going to talk more today and tomorrow. There's several talks on these verification ideas and methodologies. There's a talk on the OpenHW stand on RVVI, the RISC-V verification interface. And also, as Imperas, we're talking a lot about it and showing our technology. And actually, on Thursday, there's an hour tutorial going through a lot of this stuff. So with that, I'd like to say thanks very much for listening. And come and talk to us about verification. Thank you.